We are going to be starting off this week with this chapter 6, which is 6 in the big book. And if you have a little book, the soft cover, it will be 7. So we're going to start off with this chapter. And this chapter is all about electronic behavior of atoms or electronic structure of atoms. So basically, I would expect you guys to, read the chapters, read the theory part of it before coming to class so that you basically be able to get what the concept is talking about, and then you will have questions whenever you come to class. All right, so we're going to start off with looking at some theories that scientists came up with to describe the electronic structure of atoms. And basically, when you hear the word electronic structure, it's just talking about the behavior of electrons in atoms. So before we talk about that, we look at what we call electromagnetic radiation. And basically, it helps us to understand electronic structure of atoms. So we're going to start off with just doing a quick review on electromagnetic radiation. So if you've heard of electromagnetic radiation before in the past, maybe in your high school or anywhere else. So basically, the electromagnetic radiation is like the emission or transmission of energy in the form of electromagnetic waves. So before we get to looking at the electromagnetic spectrum, these two terms are very important. So this chapter has quite a number of terms that you expected to know. So basically, we look at the word frequency and also wavelength. So wavelength is the distance from one point to the other, and frequency is how many wavelengths, how many waves do we have. So this is electromagnetic radiation. So you expected to sort of know this electromagnetic radiation to know the main thing to understand from here, apart from looking at the different electromagnetic radiations that we have from radio frequency to gamma rays. So basically, we know that the wavelength is the one on top here, and the frequency is at the bottom here. So you can see that the relationship between wavelength and frequency is inverse, and also all electromagnetic radiation, they travel at the speed of light, which is 3.00 times 10 to 8 meters per second. This formula, you need to know this formula. And what this formula just tells you is that frequency is directly proportional to, it's inversely proportional to wavelength. Frequency is inversely proportional to wavelength. And when you remove the proportionality, it becomes C. So basically, what that is going to tell us is that frequency, we use this symbol that looks like V to represent frequency. Frequency equals C over wavelength, where C is the speed of light, 3.00 times 10 to the 8 meters per second. This symbol is new for frequency. This symbol is lambda for wavelength. C stands for speed of light. Lambda, new, speed of light. So basically, these are the different lengths of electromagnetic radiation. And basically, these are the type of electromagnetic radiations, the type and the length. So let's just keep moving again. Yes, V is frequency. All right, so we want to look at electronic properties not explained by waves. So for example, scientists discovered that hot objects could emit light, which we call black body radiation, and also emission of electrons from metal surfaces we call photoelectric effect, and the emission of light from neutrally excited gas atoms emission spectra. So all of this could not be explained by the electromagnetic radiation. So further scientists look into how we can explain this phenomenon. So we look at the nature of energy. Basically, the wave nature of light does not explain how an object can glow. So we're going to look at why some objects glow in with different colors. And the reason why they glow in different colors will kind of be explained mathematically using some theories proposed by some scientists in chemistry. So Max Planck helped us to understand that energy comes in packets, or we call them quantum. That is, each level of energy has a discrete amount of, for example, each level of this staircase has a discrete amount of energy. So let's say that this is 1 electron volt, 2 electron volt, 3 electron volts, 4 electron volts. So each energy level has a discrete amount. So that's what quantum means. And that's what the word quantum mechanics came from. Now, photoelectric effect explained by Einstein concluded that energy is directly proportional to frequency. The higher the frequency, the higher the energy. To remove the proportionality constant, we introduced the Planck's constant, which is H. So basically, energy is directly proportional to frequency. So when you remove this proportionality constant, energy will be equals to HV, where H is the Planck's constant. Okay, so energy is directly proportional to frequency, okay? And it is, when you remove that proportional sign, you bring H there. So quanta just means a packet of energy. That is, quanta just means a discrete amount of energy. A discrete amount of energy. That is what quanta means, discrete amount of energy. That is a specific energy. In simple terms, a specific amount of energy. Now let's go to atomic emissions. So again, this chapter is we're looking at electronic behavior in atoms. And before we get to the main objective in this chapter is knowing how to write electronic configurations. This chapter is not big at all. It's not that big. The main objective is knowing how to write electronic configuration, how to draw orbital diagrams. And before we do that, we got to learn some theories proposed by some scientists. So now, earlier on, it was discovered that different elements emit different light. Neon has a color of like orange. This is H. Hydrogen has a color of like lilac. Sodium is used in street lights. Sodium has a color of like yellow. It emits yellow. So this color corresponds to the wavelength by which they emit. So we're going to see that whenever you see colors, the color you see corresponds to a wavelength. All right, so I want to look at continuous versus line spectra. So continuous spectrum just basically tells us that a spectrum of light that continues. And basically, for example, we look at the spectrum of hydrogen and we look at the spectrum of neon. No, lilac is like a little bit like purple, something like purple, like light purple. So neon this is the spectrum of neon. Now, all of these can only be seen experimentally. This is just the theory part of it. So all this can be seen experimentally. If you actually do this in the lab, but this is not part of the general chemistry 1 lab. It's not part of it, but it can be seen experimentally. All right, so we want to look at the hydrogen spectrum. Now, all these lines with the colors you see represent the wavelength that corresponds to them. So basically, when the electrons in hydrogen absorb energy, light energy, they're going to emit energy back. So when they emit, then you see colors. These are the colors you see, corresponding to a particular wavelength. So this number down here is the wavelength, 400 to 700 nanometers. So basically, these scientists basically gave us this formula to be able to explain the difference in the energy level in hydrogen atom. So we're still going to do calculation. But before we get there, again, we are looking at different theories that has been explained and it has been accepted in the scientific community. All right, so we want to look at the Bohr model of atoms. So basically, Niels Bohr adopted Planck's assumption and explained the phenomena this way. So this is just take this like an atom. I know many of you are kind of used to drawing, drawing or just writing electronic configuration. For example, for hydrogen, many of you are kind of used to this and just put that as an electron in hydrogen. So let's say that this is the hydrogen atom. This is a hydrogen atom. Now we are going to see how this scientist called Niels Bohr explains how the electrons are arranged in the energy level in hydrogen. All right, so this N is what we call the principal quantum number. I know we haven't gotten there yet, but we're going to get there. N represents the principal quantum number, essentially. So all of these levels represent energy levels in an atom. So in an atom, there are energy levels. Those energy levels are where we have electrons. So we want to look at those energy levels. We want to see Niels Bohr description of the energy levels. Now, keep in mind, Niels Bohr description has a lot of limitations. That is why the final concept, the final theory that is widely accepted is the one by Erwin Schrödinger, which is the father of quantum mechanics. So we're going to look at basically the quantum mechanical description of electronic structure of atoms. So back to Niels Bohr description. This is level 1, and this is level 2, and all these levels are also there. But Niels Bohr could not really account for this level. So we're just going to stay with what Niels Bohr was talking about. So if an electron jumps from level 1 to level 2, we say before that could happen, the electron must have absorbed energy. Now, the lowest level here is called the ground state. The highest level here are called the excited states. So the ground state is where you typically find electrons. When the atom absorbs energy, the electron will move from the ground state to the excited state. Now, Ni represents the initial, that is the initial level. N again represent the principal quantum number. We haven't talked about quantum numbers yet, but again, we are going to get there. So N represent the principal quantum number. I represent the initial level, which is the ground state here. For this one is ground state. So when electrons jump from ground state 1 to level 2, it goes to the excited state. Delta E will be greater than 0 because delta E equals final minus initial. So what that means is that delta E equals final minus initial. So basically this delta E that we see here, it's how we get that is delta E equals the final state minus the initial state. This is I. This is initial. It depends on what you are considering. So I is initial and F is the final. So this is NF minus NI. So for this one, for the movement from level 1 to level 2, from ground state to excited state, delta E equals 2 minus 1, which will be equals to 1. That is why delta E is greater than 0 here. Now, whenever delta E is greater than 0, we say photon is absorbed. By the way, another name for photon, a layman term for photon is light. So whenever photon is absorbed, there is a transition from the ground state to the excited state. Now, in that case, delta E is greater than 0. So for absorption, delta E is greater than 0. So let me just kind of put a quick summary here. Let me do a summary here on the side. Photon is light energy. So, and then emission. So I'm going to explain this now. So absorption, delta E is greater than 0. Now, we haven't talked about emission. Whenever an electron jumps from the ground state to the excited state, it doesn't stay at the excited state because as the name sound, excited, it means it's excited, right? It wouldn't stay there because it's not stable there. It's just going to come back down. When it comes back down, light energy is going to be emitted. So light, you're going to see light. Whenever there's emission, you see light. And if that light corresponds to the wavelength between the visible light, you will basically see color. So this is emission. What I just showed here is emission. So emission, so basically, let me just rewrite this. So I will label this so it can be much more easier to understand. So this is absorption. And on the side here is emission. And this here is emission. Okay, so whenever you absorb light and you absorb energy, right? And you go from the ground state to the excited state, it's called absorption. So when you go from a lower level to a higher level, it's absorption. When you come back down from a higher level to a lower level, it's called emission. Now, it is called emission because whenever electrons falls back down to the ground state, it's going to emit light. When you emit light, if that light is within the visible region in the electromagnetic spectrum, you will see color. And now remember, we mentioned this electromagnetic spectrum earlier today. We talked about electromagnetic. Let me go back there. So this is the visible region. So we as human beings, we can see this visible region is we can see with our naked eye. So we as human beings, we can see between 400 and 750 nanometers. Anything outside of that, we cannot see. So whenever an atom emits light and we see it, it's got to be between 400 and 750 nanometers. Okay? So visible light is what we can see as human beings. So back to what we are talking about the concept of emission and absorption. So let me go back to that slide real quick. So again, remember, we are still talking about Niels Bohr. That scientist called Niels Bohr is theory on how to explain. So we're basically talking about, let me go back to that slide I was talking about. So we're talking about Niels Bohr is theory on the explanation of electronic structure of atoms. Okay, now we pass this place. So what we are discussing here is not classical physics, it's quantum physics. So as far as the surroundings, so we're looking at atomic, deep inside the atom, we're looking at electronic structure of atoms. So I know you guys we just talked about exothermic, endothermic, and all of those. So basically, that is explained in terms of classical physics, what we can see. Everything I'm talking about, we cannot see it because it's electronic, it's electrons. So I mean, you can use that analogy, but then when we're talking about quantum chemistry, or using quantum physics to understand quantum chemistry, we are basically talking about electrons, which we cannot see. So yeah, if you emit something, yeah, you do release. Yes, you release. In this case, there's light. All right, so the first thing that we just talked about here is that when electrons go from the ground state in an atom to the excited state, it's absorption. When it comes back from the excited state to the ground state, it's called emission. So again, all of these are not visible to the naked eye. Whenever we see the light when it emits, if that light wavelength falls between 400 and 750 nanometers, then we say that it's in the visible light. So now this is for absorption, delta E is greater than 0. For emission, delta E is less than 0. All right, so the Bohr model continues that an electron in a permitted orbit is in an allowed energy state. So an electron in an allowed energy state does not radiate energy, therefore it does not spiral into the nucleus. So basically, Niels Bohr was able to explain that electrons are in an allowed energy level. That is, electrons can be found either on level 1 or level 2. In this case, for now, this example we are using here is hydrogen. So this example is hydrogen. The example of the atom we are using here is hydrogen. So what Niels Bohr is saying is that electrons are only permitted in a certain level. They cannot be found in between the levels. So we're using this example of hydrogen, and we're going to see that Niels Bohr theory is highly limited. That is why the other guy called Schrödinger that gave us a very good description of electronic behavior in atoms is much more acceptable than this. So again, we've gone past this. There's another scientist after this. I'm just explaining this before we get to the last one. Now, so basically electrons can only be found in certain levels. Now, energy is emitted or absorbed by the electron only as electron changes from one state to the other. So this energy is emitted or absorbed as a photon that has energy. So basically, what this is saying is that whenever there's emission, then light will be emitted. And if that light falls in between 400 and 750 nanometer of a wavelength, then we can see with our naked eye. Now, that energy of the light that we can see, this is a formula we use to calculate that, where E stands for energy, H stands for Planck's constant, and V stands for frequency. So let me just kind of write this here. E is energy, H is Planck's constant. Planck is the name of a scientist. Planck's constant is 6.626 times 10 to the negative 34. Seconds. All right, so E stands for energy, H stands for Planck's constant, which is a constant, is 6.626 times 10 to the negative 34 joules second. And V stands for frequency. So what this is saying is that whenever the light emits, whenever there's emission, the energy of that emission can be calculated by multiplying the frequency of emission by the Planck's constant. Okay? So frequency times the Planck's constant. Again, we are still going to do calculation. So the last theory for the Bohr model was just 3. So basically, the summary of it all is that electrons in the lowest energy are in the ground state. So let's say this is the lowest energy, this is the ground state. The next level here, the higher energy is the excited state. So to be able to calculate the difference in energy between one level and the other, we use this formula. Delta E equals EF minus EI equals minus 2.18 times 10 to the negative 18. Now, by the way, this constant is called the Rydberg constant. This is the Rydberg constant. So this constant here, this number here that you are looking at, is a Rydberg constant, okay? and then multiply by 1 over NF, where N stands for the energy level, F stands for final, N stands for energy level, and I stands for initial. So again, we are still going to do calculation with this. So you can just, just hold on to it. We're going to do a calculation with this very soon. So the higher the energy level, or N, the more reactive the atom is, or the electrons are. No, we actually not. I mean, we are not describing the reactivity of the atom yet. What we just want to know is that whenever those electrons move to the next higher energy, they are going to come down. So, but the higher they move, the bigger the distance between them and the ground state. So you're going to see that difference in the energy. The bigger the difference between the ground state and the next excited. So let's say that the electrons move from level 1 to level 4. So basically, that difference will be 4 minus 1. The difference will be 4 minus 1 when you're looking at the delta E. So the higher the level, the bigger the delta E. The bigger the delta E. As far as the reactivity of the atom yet, we are not describing that yet. So limitations of the okay. So how you will know which one to know is that you basically it will give you the formula number 1. And then you will be given the ground state energy and the excited state energy. So you'll be given the ground state energy and the excited state energy. That one that I gave us first. So let me go back there real quick. So basically the delta E equals NF minus NI. The one I gave us was what it was that stopped here, right? This one is just it's like the theoretical concept of it. This is the main formula. This right here is the main formula. So we don't use this, we use this one. This is just like the introduction to this. So when you are told to find the delta E, this is the one you use this one as a whole. You use this whole one as a whole. Because that whole one just basically corresponds to delta F main, NF minus NI. All right, so quickly, the limitation of the Bohr model is that it only works for hydrogen. It doesn't work for helium and up. So it's pretty much not very useful. So let's just get to it. So I'm just going to kind of speed up right now because, again, like I said, we're learning all this so we can understand why we write electronic configuration and how we write electronic configurations in atoms. Since this chapter is all about electronic behavior in atoms, that is how electrons behave in atoms. So these are the important ideas of Bohr model. Electron exists in only certain discrete energy, and energy is involved when electron goes from one level to another. All right, so we also look at the wave nature of light, which is explained by de Broglie. So de Broglie sort of introduced mass into the concept, where this is the wavelength equals Planck's constant divided by mass times velocity. So, I mean, de Broglie is also another scientist that gave another explanation about electronic structure of atoms. Then another scientist called Heisenberg also gave his description, okay? So we are going to a scientist called Schrödinger. So Erwin Schrödinger is a person that developed the most recent explanation of electronic structure of atoms. Now, this concept is called, this theory is called quantum mechanics. And it's a widely accepted description of electronic behavior in atoms. Now, from what we have learned from, since I've been talking, is that the summary is that electrons are located on the energy levels in atoms. And whenever the atom absorbs energy, Electrons move from the lower level ground state to the higher level excited state, and then they come back down. Now, Niels Bohr didn't really explain where can we locate the electron on the levels. Well, it just said that electrons are on the level, but where can we find the electrons on the levels? It's like somebody said that you live in Texas. Where exactly do you live in Texas? So Erwin Schrödinger gave us a very, very good specific description of where we can find electrons in atoms. So it's like somebody asks you, where do you live in Texas? Well, you can say you live in Houston. You can say you can give them your street address. So that is the difference between what Erwin Schrödinger proposed and what Niels Bohr proposed. So Niels Bohr just says electrons can be found on the levels, but Erwin Schrödinger breaks it down to where exactly can you find the electrons on the energy levels. So that is what we call the quantum mechanics. In physics, it's called the quantum mechanics, and in chemistry, we call it the quantum chemistry. Now, it's a whole field on its own in chemistry that we're not going to, of course, we're not doing the calculations. It's all calculus. We're not doing these calculations. All we are using this to understand is to understand how to write electronic configuration. Now, Erwin Schrödinger did a very, very good job in explaining to us that electrons are not just on the energy level, but they are found somewhere on the energy level. The probability of finding an electron on the level can be found by solving the Schrödinger equation, basically. Of course, we're not going to solve that equation. So this symbol here is called the psi symbol that we can see here. It's called psi. And then this symbol basically represents the wave function. So we call it the wave function in chemistry. So the square of the wave function will help us know where we can find, if you can solve the square of this wave function, if you can solve the equation, you can basically find, you can basically know the area where you can typically locate the electrons. So we're not going to be solving the wave function, like I said. All we are going to be talking about is the quantum numbers associated with the wave function, basically. Now, the solution of the Schrödinger's wave equation for hydrogen yields wave function for the electron. So now this is just telling us that this is the area where we can find the electrons on the energy level. Now, the electrons can be found in this area. So these dots kind of represent like clouds, sort of. So it gives us the area where you can find electrons. So whenever you have a high wave function value, there is a high probability that you can find the electron. Whenever you have a low wave function value, there is a low probability that you can find electrons there. Okay? Again, we are not doing the mathematical description of wave function. We are not solving wave function. That is for quantum chemists. It's like I said, quantum chemistry is a whole field on its own. We're not doing that. So all we are looking at is what we're about to do right now. Quantum numbers. We are looking at what we call quantum numbers. These quantum numbers will help us to understand where exactly can we find electrons in an atom without having to solve the wave function. Of course, the wave function has been solved. That is why we can do this. But we're going to use the quantum numbers to understand in theory, not by mathematics, not by calculus solving the wave function. We're basically going to use the theoretical concept of quantum numbers to understand where we can find electrons in the energy. Now, I have been talking about wave function and everything. I've been like wave equation. Wave function is another word for orbitals. Orbitals is where we can find electrons in an atom. Orbitals are located on the energy level. Remember, Niels Bohr said we can find electrons on the energy level. We saw that earlier, but it didn't kind of pinpoint where exactly we can find electrons. Now, the scientist called Erwin Schrödinger was the one that gave us a mathematical description that the square of the wave function gave us the high probability of where you can find electrons. Now, the wave functions are called the orbitals. The orbitals are located on the energy levels. So an orbital is described by a set of 3 quantum numbers. So which is the principal quantum number, N, the angular momentum quantum number, L, and the magnetic quantum number, ML. We are going to talk about this. You don't need to memorize this, because when you see the questions about this, you will see that you don't need to memorize this at all. It's just, again, we're doing so much explanations. You don't need to memorize the names of the scientists as well. You don't need to memorize all of that. The objective in this chapter is to know how to write electronic configuration. We are about to get there now. Now, the principal quantum number describes the energy level on which the orbital resides. So again, remember I said Schrödinger helps us to understand where we can find electrons in an atom. It said that electrons can be found on the orbitals, okay? Those orbitals are on the energy level. Niels Bohr stopped at an energy level. It didn't tell us where exactly can we find electrons. But Erwin Schrödinger, solving the wave function, found out that we can find electrons on the orbitals. So right now we are now focused on the orbitals to see how electrons are located on the orbitals. So again, it's like you're living in Texas. We are in Texas, you're living in Houston, right? So orbitals are like, the energy level are like Texas, and the orbitals are like Houston. So we're kind of breaking it down till like we get to your street address, where exactly you live. So Erwin Schrödinger helps us to understand exactly where electrons are located on the atoms. So we are getting there. Now, principal quantum number describes the energy level which the orbital resides. The next one is the angular momentum quantum number. That should be the L. So this angular momentum quantum number defines the shape of the orbital. So the first one is a principal quantum number, which is N, represented by N. So principal quantum number is represented by N. It describes the energy level where the orbital resides. Describes the energy level where the orbital resides. Okay? Now, next is the angular momentum quantum number. This describes the shape of the orbitals. So allowed values of L are integers ranging from 0 to n minus 1. So essentially L, so n is the rings, yes. N is the rings. N are the rings, yes. So L equals to n minus 1. L equals to n minus 1. So if n is equal to 0, so basically, no, if n equals to 1, it starts from 1. If n equals to 1, then L will be equals to 1 minus 1 is 0. So the letter used is S. So basically, the letter used is S. So the value of L when it's 0 is the letter used is S, where S is an orbital. So the L basically tells us the shape of the orbital. So if L is 0, the shape is S. If L is 1, it is P orbital. Well, S orbital has a spherical shape. And then if L is 1, the orbital is P. And we're going to see the shape of the P orbital, the dumbbell shape. Then if L is 2, the orbital is D. And if L is 3, the orbital is F. So what you should know is that L equals n minus 1. So L equals n minus 1. So the last one is the magnetic quantum number, which kind of breaks down the orbital. Basically, it breaks down the orbital. So the magnetic quantum number is ranging from minus L to L, including 0. So what that means is that if L stands for angular momentum quantum number. So if L equals to 1, ML, if L equals to 1, ML will be equals to, so let me just use the other thing to write. So if L equals to 1, ML will be equals to minus 1, 0, and 1. So if L equals to 1, ML will be equals to minus 1, 0, and 1. If L equals to 2, ML will be equals to minus 2, minus 1, 0, and minus 2. Again, you are going to see the implication of all of this as we go. You are going to see the implication of all of this as we go. If L equals to 2, ML will be equals to minus 2, minus 1, 0, minus 1, minus 2. So all of this just tells us. Now, remember I said L represents the orbitals. So basically, L represents the orbitals. You don't have to worry about learning this because this is, by the time we get to the electronic configuration, this is just story. It's very, very easy. Writing electronic configuration is very easy. Now, this is just a story before that. I'm just covering the story before that. So it is not difficult at all. It is not. All right, so now this table represents all of the possible values of L and all of that. So I will just kind of explain one of them so you can understand. When N equals to 1, possible values of L is 0, and the subshell designation is 1s. So what this just means is that, remember I said L is N minus 1. Okay, how we got a maximum number of each orbital? Okay, we are going to get there. So basically, I will use this table to kind of explain. Oh, I will get the orbital for the orbital shape. So that one is set in stone. You just need to know that whenever it's 0 is S, whenever it's 1 is P, 2 is D, and 3 is F. That is just set in stone. It's set in stone. You just need to know is that. You don't have to worry about how that is calculated. It's just set in stone. 0 is S, 1 is P, and so forth. But again, you don't need to memorize it. You don't need to memorize it. So now, when N is 2, possible values of L are 0 and 1. Remember, I said that. Let me write this on top here to explain something here. So maybe this will kind of help us. So I'm just going to explain this one here. I'm going to explain the 2 here. I'm going to explain this. I'm going to explain this one here. So when N equals 1, L equals N minus 1, which is equals to 0. Sorry, when N equals to 2. Let me go do the one for 2. That one is the... Let me do the one for 2. So when N equals to 2, L equals to N minus 1, which is equal to 2 minus 1, which is equal to 1. So what we are saying is that N equals 1, L equals N equals 2, L equals 1, and ML. All of this that we are doing, again, is for us to understand why we write electronic configuration the way we write it. By the time we get to writing electronic configuration, you're going to see that this is very, very, very easy. That is the main objective. So when N equals 2, L equals 1, because L equals N minus 1. And then when L equals to 1, the ML is minus 1, 0, 1. This minus 1, 0, 1 basically represents the p orbital, because 1 represents, if you're going down here, 1 represents the p orbital. So this angular momentum, this magnetic quantum number just represents the shape. It just basically represents the orientation of the orbitals. So if the orbital is S, the value of ML will be 0, and the number of orbitals is 1. if the orbital is p, 3p, for example, 3p represents is in level 3. It's the electron. So let me start from this 2 here. If the principal quantum number is 2, that means that the energy level is 2. On the energy level 2, we have two orbitals, the s orbital and the p orbital. The s orbital and the p orbital on energy level 2. Within that s orbital, the value of ml is 0. It is 0 because s corresponds to 0. The value of ml for p is 1, 0, minus 1, because p has 3 orientation that we're going to get to. So the total number of orbitals in the shell for 2 is 4, because 1 plus 3 is 4. Same thing when we come to like this 4. 4 is the one that has up to 3 here. When the energy level is 4, there are 4 possible values of L. So here we have 4F. The 4F is the highest one, and these are the possible values of ML. So let us just move on, and then we can basically understand this further when we write electronic configuration. This is shape of s orbitals. As we go from the lower level 1s to the higher level 2s, level 3s, the size of the orbital increases, so does the energy. So you can see that as we go from level 1 to level 2 to level 3, the energy of the orbitals increases. The energy of the orbitals increases. So basically, as you can see here, the energy increases, so does the size increases. So let me just write it on top. Energy of the orbitals increases, so does the size. So as we go from one level to the other, the energy of the orbitals increases, so does the size. So take this 1 as energy level 1, this 2 as energy level 2, this 3 as energy level 3. Let me kind of draw this with the way some of us are kind of used to. So we are used to doing these circles, right? Now this circle does not represent this S. This doesn't represent this S. I'm just drawing what you guys maybe used to, I mean, the way you draw energy levels. So this just represents level 1. That would be described, yes, by the magnetic quantum number. Yes, yes. So the magnetic quantum number is the orientation. The ML is the orientation. The L is the shape. So the L is the shape, whether SPD or L. The ML is how many boxes in each shape, essentially. So for magnetic quantum number, so this one is the magnetic quantum number 1. So let's just say this is the magnetic quantum number. Well, no, the angular momentum quantum number 1. Let me go back. So the angular momentum quantum number. So this is for L equals 1. So when L equals 1, the magnetic quantum number will be -1, 0, and 1. Now, again, you don't have to get yourself all worried about this. This is where we are going to end up with. We're going to end up with just drawing electrons in boxes. That's all. Just drawing electrons in boxes. That's why we are doing all of this. Just drawing electron in boxes and being able to write electronic configuration. So again, you don't have to worry about, the mathematic part and everything. So for d orbitals, these are the shape. The L for d orbital is 2. L for d orbital is 2. And because L for d orbital is 2, the magnetic quantum number for d orbital is 5. That is why d orbitals has 5 boxes. So we have -2, -1, 0, 1, 2. That is why when we draw our d orbital, we essentially draw the orbital to have 5 boxes. We're going to soon start doing that. What goes in these boxes are nothing but electrons. And once you know your atomic number, you have your periodic table, you can place electrons in the boxes. That's how simple it is. Once you know the atomic number, if you are told to draw the orbital diagram for oxygen, we all know oxygen is number 8. You just place the electrons from the lowest level to the highest level. So the d orbital, this is the d orbital. It has 5 boxes because there are 5 orientation in the magnetic quantum number, which is from the angular momentum quantum number 2, which is from the angular momentum quantum number 2. Now, these are the orientation for the d orbitals. Again, don't worry about memorizing this whole thing. Nobody asks you to draw anything. So it's just for you to write the electronic configuration. Now, the f orbitals are so complicated, we're not even going to talk about it. So let's just go inorganic chemistry to talk about that. If you have interest, you can read books on inorganic chemistry. Now, this is where we are going. This is where we are going. We want to start learning how to write electronic configuration. To be able to write electronic configuration, there are some things that we need to understand that we've been talking about, and there are some rules that we are going to follow as well. For a 1 electron atom, hydrogen atom, this is basically what the electronic the energy level looks like. You can see that this is 1s, and this is level 1, which has a 1s orbital, level 2, and level 3. But this only works for hydrogen. So here, n equals 1 has 1 orbital, n equals 2 has 2 orbital, 2s and 2p. n equals 3 has 3 orbital, 3s, 3p, 3d. Remember that it has 3d because L equals 3 minus 1, which is 2, which corresponds to d. So essentially, that little table that we saw initially, that 0 corresponds to S, 1 corresponds to P, and then 2 corresponds to D, and then 3 corresponds to F. So this is basically, just got to remember this. So whenever is 0, we have 1s. This 1 represents level 1, energy level 1. S represents orbital S on energy level 1. This 1 here, of course, represents this energy level 2 here, but no, this 2 here represents energy level 2, and then here we have 2s, 2p. So 2 represent that this energy level 2, and then the s is the orbital on energy level 2. So by the way, these are all the angular momentum quantum number. These are the angular momentum quantum number. So all of these are the shapes of the angular momentum quantum number. So now the orbitals that are on the same level are called degenerate. They have the same energy. Now this is basically what we need to be able to understand how to write electronic configuration. You will not need to memorize this at all, because to write electronic configuration is one of the easiest things. I just don't want to jump to it. That's why I'm going through all of this. The last thing we're going to do is very, very easy. So now 1s, 2s, 2p, 3s. So P, D, and F are subshells in a certain, yes, they are sort of, they are subshells in a certain arrangement, yes. So basically we have 1s is the lowest energy level, followed by 2s, 2p, 3s, 3p, 4s, 3d, 4p. Did you see how they are going from top to the from bottom to top? As they are going up that way, that is how the energy increases. So whenever you want to write electronic configuration, that is, when you want to place electrons in an atom, you don't start from the highest energy, you start from the lowest energy. So subshells just is another word for the orbitals. Subshell is where the S, the P, the D, that we place our electrons. So we place our electrons in these boxes. So if I say write electronic configuration for hydrogen, I will place my electron here. I will place one electron here. We usually place electron like arrow going up. So the electronic configuration for hydrogen is 1s1. It's 1s1. And then we go on and on. But you don't have to memorize that chart I just showed us. To write electronic configuration, all you need is your periodic table, nothing else. And I will show us how to do that. The spin quantum number just tells us that when you place electrons in a box, so this is, for example, let's just look at an X box. Let's just look at a 1s. For example, helium. Helium is the electronic configuration for helium is 1s2. So when you place electron, you place one going up when you draw the orbital diagram and another coming down. That is because the spin quantum number is how we know that. It's got to be up and down because they are both magnetic. So one has to go down, the other one go up. Go down and go up. So we don't place them in the same direction. So now we want to look at how to quickly write electronic configuration before we finish today. The law, the principle, the rules that we're going to be looking at before we start writing electronic configuration. One of them is the Pauli exclusion principle, which says that no two electrons in the same atom can have the same set of 4 quantum numbers. We are going to see that. This means that every electron in an atom must differ by at least 1 quantum number. Now, there are other rules that we're also going to look at. The next one will be Hund's rule. So, Hund's rule is not described here. Well, what Hund's rule just basically says is that the most stable arrangement of electron in the subshell is the one with the greatest number of parallel pins. So we will talk about that. We'll talk about the Hund's rule later. So now, this is where we are going in this chapter. This is the main essence of this chapter. To understand how and why we write electronic configurations. We write electronic configuration by using all those quantum numbers we have learned. And basically, when we write electronic configuration, we are placing electrons on the energy levels in atoms. Remember, we have learned that the energy level is like you live in Texas. The orbitals is like you live in Houston. Those subshells that we now saw, like 1s, 2s, are now talking about your street address. So we basically break it down to which level can we find electrons, which orbital can we find electrons. So basically, for example, let me go to the next one here to make things fast. So I'll use this to kind of explain the electronic configuration, how we write it, and what we need to understand from writing it. So whenever we write electronic configuration, we are basically placing electrons on the energy level in an atom. So 4p5 is an electronic configuration where 4 represents the principal quantum number n. So this represents the energy level, which is the principal quantum number n. So this represents the energy level. Energy level. All right, this represents energy level. Now, P represents the type of orbital, that is S, P, D, or F. P represents the type of orbitals, that is S, P, D, or F. So P represents type of orbitals. That's also called like the subshell. So P represents the type of orbitals like S, P, D, or F. And then this number 5 represents the number of electrons in those orbitals. Remember, with everything we have been saying since morning, we are trying to just place electrons in their house where they belong. Just like everybody live in their house. So this is electrons. So the electrons, they live somewhere. They live in the orbitals, and the orbitals are residing on the levels. The electrons live in the orbitals live in the levels. Just like we live in Houston, I mean, wherever you live, good at Houston, and then, I mean, the Houston is in Texas. That's just what this is all about. All right, so let's just go to drawing orbital diagrams. To draw the orbital diagram for lithium, so basically lithium is number 3 on the periodic table. So to be able to draw the orbital diagram, we just basically draw these boxes. Now, before we get here, we need to do the electronic configuration first. That's where you can understand that other one. Okay, now here comes Hund's rule. So we're filling the generate orbitals. Hund's rule is one of the rules that we need to learn before we actually go into writing electronic configuration. When filling the generate orbitals are orbitals with the same energy. The lowest energy is attained when the number of electrons having the same spin is maximized. So what that means is that if you want to fill, for example, if you want to place 3 electrons here, so let me quickly explain Hund's rule before we go ahead and learn how to write electronic configuration. So if I want to place 3 electrons here, if I want to place 3 electrons in the p orbital, now this is the p orbital. We know that p is the one that has 3 boxes. D is the one that has 5 boxes. F has 14 boxes. S has only 1 box divided in, that can hold 2 electrons. So if I want to place 3 electrons here, so if I want to place 3 electrons in this p orbital, so what Hund's rule is saying is I place them singly first before I start pairing. So let's say I want to place three electrons, I place them. Let's say I want to place 4 electrons. I will first place them. Did you see how I place everything singly? Then I come back in and pair it up. Then I come back and pair it up. So this is if I want to place 4 electrons. So this is how we place electrons. According to Hund's rule, you place them singly facing the same direction before you come back and start pairing up. All right, so to be able to write electronic configuration, you are going to need your periodic table. So you are going to need your periodic table to be able to write electronic configuration. When you have your periodic table, did you see that this looks like our periodic table? Our periodic table, even though it is not kind of color coded, it is broken down into blocks. Okay, go back. Yes, what was the question? Okay. So our periodic table that we use is broken into blocks. The one on the left hand side is called the S block. So I'm going to show the periodic table for us to be able to know. As a matter of fact, let me show us the periodic table. Let me go ahead and quickly show us it. So I hope you guys have your periodic table. Once you have your periodic table, you can write your electronic configuration. You don't need to memorize anything at all. At all. Because the periodic table is designed to be able to write is represents a block. So I'm just going to go there real quick so that we can see what I'm talking about. So this is the periodic table, right? Did you see this first two? This is the S block. This is the S block. It's called the S block. This middle, the transition elements, this is called a D block. And I'm going to explain exactly why this is called a D block. Let me finish writing this first. This right here is called a P block. You can label yours. I mean, if you have yours, you can label it. And this right here is called the F block. I'm going to explain why this is called the S block. Remember we said that the S orbital is just one block, right? This S orbital is just one block. And this one box can hold 2 electrons, right? It can hold 2 electrons. The S orbital can hold a maximum of up to 2 electrons. That is why the S block has 2 boxes. Each box holds an electron. The D block, remember we said that the D orbital has 5 boxes. The D orbital has 5 boxes. So each of the box can hold 2 electrons. Each of the box can hold 2 electrons. Let's do that before we come back and pair it. So it should be full arrow. I'm just doing that to be fast. So each of the box in a D orbital can hold 2 electrons. That is why in our D block we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, corresponding to the 10 electrons a D orbital can hold. Does that make sense? There are 10 boxes in the D block on the periodic table because the D orbital can hold 10 electrons. See, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now let's come to the P orbital here. The P block represents the P orbital. The P orbital can hold 6 electrons total. Can hold 6 electrons total. That is why the P block has 6 boxes. Each box can hold 1 electron. And lastly, the F block. So before I do the F block, did you see that P orbital has 6 boxes? 1, 2, 3, 4, 5, 6, corresponding to the 6 electrons that P orbital can hold. 1, 2, 3, 4, 5, 6. Lastly, the F block corresponds to the F orbital. The F orbital has 7 boxes, which can hold 14 electrons. 1, 2, 3, 4, 5, 6, 7. Which can hold 14 electrons, corresponding to the 14 box F block. So once we know this fact, you can write electronic configuration without having to memorize anything or look it up online. So this is basically can hold 14. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. The F block corresponds to the F orbital, which can hold 14 electrons. If I ask you now, write down the electronic configuration of boron. the electronic configuration of boron will be 1s2. Now, whenever we are writing this electronic config, now let me go back to the file. Let me go back to the file so that you can see exactly the 6 lectures. So you can see exactly the blocks and how we write electronic configuration. So to write electronic configuration, all you need is your periodic table. It's one of the easiest things in this course. All you need is your periodic table. Once you can pinpoint where the atom is, then you can write the electronic configuration, because wherever an atom is, wherever an element is, will tell you, I mean, they are the last orbital that you can find them. Tell you, because where an element is on the periodic table is where it's living. So it will tell you the orbital where you can find it. So let me go real quick down, all the way down to where we stop right now. So right now we are going to write the electronic, well, before, let me quickly go there. We're going to write the electronic configuration of boron, and then we write 1 or 2 more before we stop today. And then when we come back on Wednesday, we round up this chapter, and then we move on chapter 7. This chapter is not that big at all. Okay, so I'm just going to kind of show it this way. All right, this is a periodic table. Now, basically, the F block is kind of sandwiched here. Now, we all remember that the F block at the bottom of the periodic table is supposed to be here. I mean, in reality, it's supposed to be here, but scientists pulled it down because it's going to make the periodic table to be too wide and not that concise. So they pulled it down. So this is where the F block is on the periodic table. Now, let us go to here. All right, so this is the blocks I just showed us. Now, this is a color-coded one. I just showed us the one that we have for the exam, right? And I kind of section it off for us to know which block goes where. So this is the S block, this is the S block, this is the D block, this is the P block, as you can see, the color code, and that is the F block. So if you want to write what element is here on the periodic table, what element is it? Did you see where my color, where my dot is? Let me use another color. What element is here? Anybody knows? So get your periodic table out and tell me what element is here on the periodic table. Did you see where this pen is? Which element is there? Okay, very good. So because we know this is hydrogen, helium, right? Lithium, beryllium, boron, right? Good. If I want to write the electronic configuration of boron, that would just be 1s2. Now keep in mind, this is helium. Helium should be here, but of course, we always keep helium with the noble gases. This is where helium should be. So to write the electronic configuration for boron, that would just be 1s2. Now remember, I've talked that S can hold a maximum of 2 electrons. 1s2, then 2s2, because, well, there's something I didn't mention. Boron has 5 electrons, right? So in case you are wondering, how am I putting the numbers? Those numbers I'm putting on top represent the electrons. Boron has 5 electrons. So this is my short form of electrons. Yes, so yes, you are correct. So 1s2, 2s2, and then 2p1, exactly. Yes, exactly. As a matter of fact, that is a question in an exam. You can add it together to find the exactly. 2 plus 2 plus 1 is 5. Does that make sense? So can we write what is the element here? What element is here? What element is where I put my purple dots? Okay, somebody asked, why can't it be 1p1? Okay, just look at this. Boron is on level 2. So the last level got to be 2. The first level of boron is 1. So we filled up that first level, 1s2. The next one is, so we are traveling here. See, we are going from 1 and we are traveling up here. So to get up here, we are placing the electrons as we go till we get to here. So we place our electron in those little blue boxes, which is represent the s orbital 1s2. Then we come here, 2s2, because each of these boxes represents an electron. So it's like we place one electron here, another electron here. Now this should be here. Just keep in mind, this should be here. It's just brought there because helium belongs to another electron here, another electron here, another electron here. There we go, boron. That's boron right there. So boron is 1s2, 2s2, 2p1. If we have to go down all the way to the yes, so this is fluorine. So what would be the electronic configuration for fluorine? So again, we are traveling down to fluorine. So in this case, we are traveling down to fluorine, and we are placing the electrons on the orbitals till we get to fluorine. So that will be 1s2. So that will be 1s2 because we go from level 1. Exactly. So we have 1s2, we have 2s2, and then we have 2p5 because look, fluorine is here. 1, 2, 3, 4, 5. 2p5. Exactly. So this is for fluorine. 1s2, 2s2, like that. So basically, we go all the way like that. We go all the way like that. So the total of that is 9. So this is for fluorine. This is the electronic configuration for fluorine. So I'm going to stop here because of time. At home, you can try all the way to number 20. Try writing all the way to number 20. For 2p5, it is because it's 2 down p because it's in the red, and 5. Yes. Because the fifth one is in the red, and it's level 2. So we're in level. So we started from level 1. We walked our way up to level 2. So for the level 2, we got to pass 2s before we get to p. So that's why we have 2s2, then 2p5, then 2p, 1, 2, 3, 4, 5. For this last one, neon, it will be 2p6. If we were to do neon, it will be 2p6. Neon will be 2p6. So that's how we write electronic configuration. So at home, try to write electronic configuration for all the elements from number 1 to 20. So stop at calcium. So write electronic configuration from number 1 to 20. Yeah, when you add the one for fluorine, it's 9. When you add the one from neon, it will be 10. Remember, neon is here, right? So when you add fluorine, it's 9. When you add neon, so let's say this is neon, right? When you add the one for fluorine, it's 9. When you add the one from neon, it will be 10. So essentially, when you add those numbers on top, you have the number, the atomic number back. So basically, that's just how we write electronic configuration. And that's the main objective in this chapter, knowing how to write electronic configurations. So you can see that, all you need is your periodic table and you can write. When we come back on Wednesday, we kind of look at how we write the D and also the F, because it's kind of different the way we write the D and the F because of this change in level. So I'll see you guys on Wednesday.